So welcome everyone to another webinar for BART. Today, Professor Martin Ucker's group with Moritz and Jason are going to present some of the additions they've made to BART on the side of deep learning. I think it's really exciting to see how flexible BART can be, and really it's another useful backend for doing not only conventional MRI but also now deep learning MRI. And the really nice thing is that you can do both of them really seamlessly together. I think that's really where these tools shine, is that they're really built for MRI recon and MRI research. And so we're bringing the deep learning tools into it, as opposed to bringing the MRI tools into these frameworks that weren't really designed in the first place for them. So really excited to hear what they have to say. I'm going to paste in the chat one more time the link to the webinar materials, as well as Google Colab, which is a way you can follow along interactively. All you need is a Google account, and it will let you run the demos as they present them. It will also give you GPU access, so that it should be fairly fairly quick, which will be useful for these. So without further ado, I'll hand it off to Moritz. And again, we encourage interactivity. So if you have any questions or any comments, please feel free to unmute yourself, and we'd love to hear. And I'll be in the background, also taking questions in the chat and interrupting when needed. All right, so thanks very much.
Yeah, thanks, John. Jason, good to meet you. Yeah, very welcome to our demo here on the deep learning side of BART. And maybe a first thing, we just uploaded some preprint which describes the technical details. So it's called Deep Learning with BART, and maybe you can look into that if you want to see some implementation details. We will also update the Jupyter Notebook to include that link. But now let's start with our demonstration of the BART Reconet command. So I assume you can start from this webinar GitHub landing page, and then we can just do open and callup to start with the tutorial. And let's go to full screen mode. So yeah, that tutorial, it will be about the reconet command in BART, and that is a command to learn and apply also physics-based neural networks. So if you're familiar with BART, you can then just call BART reconet, select the network. So for example, here the Variational Network, say, okay, I want to train that. And you will need to provide some case-based data and the estimated coil sensitivity maps and some reference reconstruction. And it will.
Moritz, sorry to interrupt. Do you think you could make your text a little bit bigger?
I think so.
All right, that looks much better.
Maybe like that. Okay.
Yeah, perfect.
Thanks. So yes, we can train the reconet command. So if in the train mode, we will create some weights which describe our neural network then. And then afterwards, we can apply the neural network. And again, we will need to supply some case-based data, the estimated coil sensitivity maps, and now the weights to get the output reconstruction. This notebook here, we want to have some self-contained example how we can use the reconet command to train an actual neural network and also to apply that. And we did that based on some data from miidata.org. And so we go through it, we will download that data, and we will estimate the coil sensitivity maps with the spirit, and then train the neural network and also apply that. So maybe some first setup. So if you follow me on Google Colab, we will set some, I think I trust my notebook. We will first set some environment bubbles saying that, okay, we are on Google Colab, because then we need some different setup for BART. So that's fully self-contained here. So then there's a problem with some GPUs on Google Colab that they don't support CUDA 11. And if you're unlucky and get some of them, we will just downgrade CUDA by running that cell. to Q.Zen, but then it works also with BART. And actually what we do here is also for early setup, we just check out the BART webinar GitHub to get that to our Google Colab and also change directory into it. So when that's done now, we are in that demo1 reconet directory, which for some reason already contains BART. I assume that is because I did not fully reset my my environment. But okay, so we checked out. We are now at the current working directory. We are in webinar 6, or now we are in this webinar 6 directory of the GitHub. You could just check out. So that's just the setup for Google Colab. Then we don't have time to do a full training here. So we set the demo mode to 1, that environment variable, but you could set it to 0 and then just perform the whole training, download more data, do the full training in this notebook. But maybe it won't run on the Google Colab free version because it takes some time and there might be timeouts. So maybe you want to do that then on your local system. Yes. And here we don't change anything. So that was the early setup. Now we come to the next thing. We need to set up BART. And yes, as we are on Google Colab, we just install it on Google Colab. Therefore, we first need to download or install the required libraries. So, for example, FFTW3 or OpenBLAS. And that went really quick. And in the next step, we just check out the BART directory. I'm confused why that is all so fast now. Just interrupt me if it's slower for you. So
it's a little bit slower on my end. I think when you run it once, you might save it to your Google Drive, and that might be why it's already downloaded.
I think so. Yeah, but actually here,
although you remove it, yeah.
I remove it and go back to it. So I'm a little bit confused why it's so fast. So, but maybe now that takes hopefully some time. So to have it in the real world case. Yeah, okay. Now the next step is that we need to compile BART. So okay, we change directory to BART. We set some compile options. And here the important thing is that we want to run with CUDA. We can run in a non-deterministic mode. Non-deterministic here means that, like, if we are on the GPU, we can have atomic operations which make, depending on how fast some thread is, we will get slightly different results from the floating point arithmetic. So we allow that to be faster, but you could turn it off to be 0. But that is no guarantee that everything in BART is deterministic then in the sense of the same operation order. Yeah.
So is that something that you recommend users set to 1 always if they're not concerned about exact reproducibility?
Yes. Mm-hmm. So I would suggest that, but so I can guarantee if you use it and use convolution that your results won't be bitwise reproducible or are not expected to be bitwise reproducible. But if you set it to 0, there's no guarantee that it is bitwise reproducible because there might be other operations which are not turned off by setting that to 0.
Is it possible to do something like stochastic gradient descent with the deterministic setting on? So, you know, have the same seed every time?
Yes. So the seeds are deterministic, I think. So even, I mean, that non-deterministic mode, it's only related to parallel operations where some operations are not associative. So if there are like different threads are differently fast, they accumulate in a different order, and therefore you get non-deterministicity. But all the seeds in BART, I think, are set deterministically. So the Gaussian, or like some random drawn numbers should be deterministic. But maybe here somebody else from the BART side could comment on that if I'm saying something wrong there.
I have a question. This is still on the non-deterministic stuff. How do you ensure that the answers are accurate with the atomic operations if you're allowing them to accumulate in different orders?
I don't think that accuracy should, I mean, which order should be accurate? We anyhow do float point precision. So either order might be inaccurate, right?
Yeah, I would say so too. Right? The order doesn't make it less accurate, but it just makes it less deterministic if it arbitrarily orders the operations. So it's a long-term aim to get fully deterministic results for everything in BART, but this flag only addresses some part of the problem space. Let's say it like this. So you get, for certain stuff, you get deterministic results if you set it to 0 at the cost of some performance.
Yes. So, but that's also only related to GPU algorithms. Yeah, welcome. Okay, now we have compiled BART. It took now here 50 seconds. I think on your system or on our local servers, it's much faster. Also part of the setup is that we set the environment path to BART so that we now can call in our bash threads just BART. And we see here, we just called BART, which we just download in this webinar directory, and it's some version 0.7, and here we see the git commit. Here, the final part of the setup is that we define some plotting function. We will some interactive plotting function we will use later. Okay, so now we are again. Oh, I don't want to go to standard runtime. We are here that we have the variational network, and we want to train that with the Reconet. We have now BART, and it is very flexible, but what it implements, for example, are the variational network and the Modal network. So the variational network, it's some unrolled gradient descent algorithm for reconstruction. So we have some initial reconstruction X0, which is usually the adjoint reconstruction or the zero-field reconstruction in the Cartesian case. And then in each iteration of this neural network, we do a gradient step with respect to the data consistency term, and we do some network update, which also represents the update due to a gradient of some learned regularization. In the Modal network, we in each iteration, we first update the current guess of our reconstruction with a neural network. And then in the second step, we impose data consistency by some proximal mapping. So yeah, we try to find the best solution solving the data consistency, and it should be similar to the guess of our neural network. Yes, and as I said, we have the BART reconet command to do that. And again, I think I already announced that in the beginning. So the first thing you should do if you see a BART command, you can run the help. So BART reconet -h. And if you scroll here far to the right, there are many options, but then we see again what we need to provide at least. So some case-based data, the sensitivities, the weights, and the reference, or if we apply it, it's the output of the BART reconet command. And then we see here the options. So the first three options define our mode. So we are in the train mode, evaluation mode, or the apply mode. but we have further other options which we might discuss later. So, but for now, we want to do the training. So the first step, what we need to do is we will obtain some case-based data. As I said, we will download them from miidata.org. And what we here do is we define environment variables again, which say us which patients from the data set we use for training or for validation data. So if we are in the usual mode, we will just use for train data patient 2, 3, and so on to 14, and for validation patient 19. But as we don't have time now to download all the data in the demo mode, we just restrict to patient number 19. Yes. So,
Moritz, quick question.
yes.
On the Reconet, you were showing the A operator for Cartesian case space, but is it possible to also use this tool for non-Cartesian data?
Yes. So it is the last chapter of that notebook. If we get there, we can use it for non-Cartesian data. Yes.
So that's really one of the niceties of this, is that you're inheriting all of the BART tools, and they all just work out of the box with this new Reconet command.
Sorry, but when you got the message about GPU or standard, which did you select?
Keep the GPU. Okay. Don't switch to standard, because then everything will be slow or fail because we say BART to use GPU. The setup takes some time where we don't use the GPU, so Google asks you to switch to CPU if you don't need it. Okay, so what I just ran in the meantime, the code is I downloaded some data from miidata.org. So this patient 19 from the Variational Network publication, and that the link is given here. And it was quite fast because Google and Amazon are connected quite fastly, I think. And in the next step, we use the BART ISMRD tool to transform this ISMRD file to some BART specific case-based data. So the CFL format. But maybe so you could also do that with Python or something else. And I would say the BART support for ISMRD is, let's say, limited and experimental. So, but it works for this data. The next cell here, we could just run, but it does not do anything. And the reason is that this cell will download all the other data and transform them. But right now we only work with patient 19, so we skip it in demo mode. I can also show you like what we have created now here on the side. So that's the reason why everything was so fast. I have some, like I was already in the BART webinars folder, and then in that BART webinars folders, I checked again out BART. So I hope that the other stuff works still. So, okay, what did we just download? No, we did not download that. I'm sorry. Where did it go?
So on my screen, I see a demo 1 Reconet archive coronal PD, and then I see some files there in coronal PD demo. Is that what you're expecting to see?
That is, yes. So actually we want to have an, yes. So, sorry, I'm a little bit deeper now in that folders, but you should have that archive folder more at top level. So what we have here is we have that is the downloaded file, and the header and the CFL file is what we just converted for case-based data. So that is now in the archive folder. So there you could download also the other files. In the next step, we just have that full K-space, and what we do now is we extract some central slices. So in the demo mode, we just extract 5 slices, so slice 20 to 25. Otherwise, you would extract 20 slices. I just run that, and that should give you now in the demo folder, Corona PD demo, this patient 19's K-space, and it's still oversampled. So from that data, the next step is, so we have the K-space. The next step is that we estimate the coil sensitivity maps. So we use the BART-Toolbox command for that. And that cell, which is the next cell, it just loops here over all patient. We just downloaded, so in our case, just patient 19. And then it loops over all the slices in the patient. And for each of these slices, it just estimates the coil sensitivity maps, and afterwards just joins them to create one file, the coil sensitivity maps also still oversampled. To speed that a little bit up, I would recommend to use here the -G option to get it run on the GPU. If you're on a local system with multiple CPU cores, you could also run that in bash subshells in parallel or do something else. But here I would recommend to add the -G. So that's the first time we use the GPU. And it might take some seconds, like 30 or 40 or so, and estimates us our 5 coil sensitivity maps.
Let's pause here for a second, because I think there's a lot of nice detail here. For one, this really shows a nice way of how you can use bash scripting to do something like estimate coil sensitivities for multiple slices, right? The callup tool on its own is not really intended to estimate the sensitivity maps for independent 2D slices, but this is a nice example of how you would do that. Another nice thing here is you can see the -A option, which automatically chooses the thresholds for eSpirit. eSpirit has two parameters you have to hand pick, and this -A will pick them for you in kind of an auto-calibrated mode. So that's also a really nice useful tool. And actually this -G, I think this is a very recent kind of upgrade that you guys have done to bring it back to the GPU. So we've always had GPU support for eSpirit callup, but now it looks like it's working quite well. And so is that something you would recommend users use if they have GPUs?
I think on a multi-core system, I would more go for the CPU version and just parallelize it. So what one could do is something like that. And in that way, we would just compute all the slices on parallel on multiple CPU cores, because we suspend that process estimating the coil sensitivity maps on one slice. We do that in parallel. And then here we just wait for all to finish before we back join the data. Yes, I would use it. So for me, it was usually faster if I have multiple cores available. But you can also run that on a GPU.
Mm-hmm.
And here we just have one CPU core, but a GPU, so GPU is faster and do it sequentially. Okay, so now the command is also run. We see now we have patient 19 and we have the coils still with oversampling. So for training, we don't want to have that oversampling, so we just remove it with BART. What we do here is, again, we loop over patients. We have now only one. Then we want to remove oversampling for the K-space, but also for the coils. So the first step is removing frequency oversampling for the K-space. So we do inverse Fourier transform to obtain the frequency oversampled coil images. The second step, we resize to the center and then do back a Fourier transform to have the K-space without frequency oversampling. for the coils, we just need to resize to the center. And I think that's also is pretty fast. I hope at least. So again, it's bash scripting and it's done. So if that updates here, you see we have the coil images for patient 19, we have the coils, and we have the k-space without oversampling. Yeah, and then the final thing of the pre-processing of the data is that we define some ground truths reference reconstruction. We still work with a fully sampled k-space, and we can use the BART-FMAC tool to do a coil combined reconstruction. So we use the coil images and multiply with the complex conjugate of the coils. And then with the -s option, we can sum along the coil dimension. So let's see what we get. I hope that this works. Yes, it also works with the other folder, with the different working directory. So yes, what we got is we have the coil sensitivity maps here. We have the fully sampled coil images and the fully sampled reference reconstruction. And you can see here we have, like in our data, still 5 slices. So with this, we can go through the slices and see the different images. Okay, so far everything was fully sampled, so that's kind of boring because we don't need to use deep learning for fully sampled data. But what we want to do is we want to reconstruct data from undersampled data. So we retrospectively undersample with some pattern. We first create that pattern. That cell does it, and here I would say, okay, bash command line tools are not that nice compared to maybe a Python function, which would give us that in maybe a few less better readable lines. But it works to create a pattern also with the BART tools in the bash scripting. And I don't want to go into the details. The final thing is that in our working directory, we have the pattern.
One thing to mention here is that there's no restriction to use the command line tools here. You could mix Python directly in this collab and save write a CFL for the sampling pattern at the end.
Yes.
Is that right? Yeah.
Okay, so we have now that pattern. So what we can do is we can do some CG sense baseline reconstruction. So we use the PIX tool. So I just start running that cell because it also may take some seconds. But what we do is, okay, we now loop over all patients in the validation data. And then we multiply the k-space data of each patient with the undersampling pattern to get some subsampled k-space. And then again, we need to loop over all the slices as to reconstruct all the slices independently. So we loop here over all the slices and then call the BART PIX command. We provided the pattern, and okay, that is not important, but we also provided the k-space, the coil sensitivity maps, and we get some output reconstruction. And in the end, we join that. So what you will get then looks like that. So here's our undersampling pattern. We have some auto calibration region in the center, and then I think R equals 4 undersampling outside. Here is some zero field reconstruction, suffering a lot of undersampling artifacts. Here's the CG baseline reconstruction. It's a little bit noisy, but still reduced undersampling artifacts. And one could, of course, go better by using regularization in the PIX tool. And again, here our reference reconstruction. So now what we have is some undersampled k-space data. We have the coil sensitivity maps, and we have some ground truths. So we can join the training data set we then provide to our reconet command. So yeah, that cell, it just says, okay, the environment variable train k-space, we just give it a short name to access the training k-space with this name, trn k-space, and the same for validation data. And the next step, what we do here is we use the BART join command to now join all the patients which correspond to the training data set along the slice dimension. So if we would have now more than just one patient, we would just create one huge data set containing all the case-based data. And what we do in the second step is that we move the slice dimension 13 to the batch dimension 15, as that is what the BART reconet command expect. So I just run that cell, and we do the same also for the validation data. And what we get is, you can see here, we get some, so we can show the dimensions of the training case base, the train core sensitivity maps, and the train reference. What you see is, okay, we have 320 times 368 dimensions. We have 15 coils, but not in the reference. Of course, that is just one image. And in the end, we have a batch size of 5 because we extracted 5 slices from one data set. But if you are not in the demo mode, you will get here something like 240 slices in the batch dimensions of different patients. And again, we can just visualize that. So we have the case base, the coils, and the reference. Okay, so now we are really done to do our first training. We use the BART reconet command.
Let's pause here just for a second. There's one quick question, which I think you'll probably answer pretty soon. Julian is asking how a PIX with regularization like wavelet will end up comparing to the machine learning based approaches. So is that something that you will show in the end, or can you comment on that?
I won't show here for the comparison. Probably you should look into the papers depending on, for example, for the variational network. I mean, they see slight improvements. I think training helps, but
so Moritz,
also, yeah.
Sorry to interrupt. So one thing, if users are interested, you don't need to do this now, but you could scroll up to the CG Sense baseline and add a -L1 to there, and you would see what the compressed sensing reconstruction would look like. Yes. And that would be an easy way to compare. And that's one of the nice things of BART is that just by changing the flag of the PIX command, you can switch from CG Sense to L1 wavelet to total variation. So you could play around with that as well, the cells higher up.
Yes, thanks, John.
Yeah. Any other questions before we keep going?
One stupid question is, I cannot see the folders in the same way you have on the left side.
I hope that you see in the direct webinar 6 demo Recognite that you see there some folders.
Yeah, but I don't see the first, the parent, so the BART webinars.
That one.
Yeah. Anyway, it's yeah. I don't have that.
But you see folders here?
Yeah, I see other folders, but not them.
Which one? Like also sample data, or?
I see bean, boot, content, data lab.
Okay, maybe then, I mean, that's probably that one. And if everything worked, then from here you can go to content and then BART webinars.
Yeah, I don't have that folder. I have one that is BART and same sample data, but not BART webinars.
I just assumed that you missed some cell in the beginning doing the setup.
Yeah, maybe.
So
okay, I don't want to.
Can rerun.
Yeah, I think it's not important.
For that.
Please go ahead.
Yeah, try rerunning from the start, and one of the steps is to download the BART webinars Git repository, and that would create that folder for you. So it's possible that was missed.
Yeah.
And then there was another question in the chat: is if the reconet command would work in MATLAB as well?
Not that nicely. No, there's some problems with the MATLAB wrapper. So you will need to write the files to disk manually. You cannot use the MATLAB wrapper. That there is some reason, because it does not follow everywhere the usual BART structure. Because if we train the output, so the train ref is some input and the weights is an output, and I think the MATLAB wrapper would only expect the last argument as an output. And there's also a thing like that we store multiple CFL files at once in the weights, and that's probably also not covered by the MATLAB wrapper. I'm sorry for that.
I have a question.
Yes.
Does it expect to put all your training data into like one file? If you have like thousands and thousands of images, is there like a limit on the file size or the loading RAM, or to being able to load all this data at the same time?
Yes. So first thing, yes, it expects to use to put everything in a file. You could, with the bash script, just write a loop which just loads one data set, trains for some steps on that data set, and then goes to the next data set and trains for some steps on that. The file size problem, I mean, we currently, so we use memory mapped IO. So the coil sensitivity maps, for example, they will just be read from disk if they don't fit in RAM. That would work. For the reference, the same. So, but currently it expects everything in one file. But that might be something we can change in some future. Yes.
Yeah, those are both good feedback. You know, the MATLAB support and also ways to make training with lots of data more flexible. You know, this is a tool that's fairly new, and so we'll definitely look at adding features that you all think are helpful.
Yeah, thanks. Okay, then we might go on. So here I just wrote in the comment the BART reconet command we will just call here in the next cell to give comments for the options we used here. So again, BART reconet is a command. We choose the network, the variational network. We can, I mean, that would be also the default option, but we can specify the number of iterations, which is 10. We say train, okay, I said that already. We use a batch size of 2. That's here related because our whole training data set has just batch size of 5. So we cannot really use a much larger batch size. Okay, we choose the --GPU option to run on the GPU. We normalize the input data automatically. So we will compute the adjoint or zero-fade reconstruction and then normalize such that for each slice, the maximum magnitude of that is 1. That would be also default option, but for that, I mean, we start here with a very, very simple training, which just runs on 1 patient. So there we also just run for 1 epoch. And then the next step here, we also provide a pattern, the training pattern, which we just created. And the reason is basically that the file with the training case base is still fully sampled, but in the pre-processing, it will multiply the fully sampled case base with a training pattern to simulate the undersampled data. Therefore, one could use different patterns on the same training case base data. Yes, I just run that cell. And yeah, what you see here is the neural network. So that is one operator it just created to train the neural network. It has some inputs, number 7, and the inputs are the reference reconstruction, the adjoint, the coil sensitivity maps, the pattern here called point spread function, and then the weights lambda. So that's the gradient step size of the variational network, the convolution weights, and the weights for the Gaussian radial basis function. So you might want to look into the variational network paper to understand what these weights are meaning. But yeah, so that is what are the inputs of that neural network operator, and the output is the mean squared error of the magnitude reconstruction here. So that neural network operator basically represents that loss that we try to minimize, and that is then what our training algorithm does. So here, as I said, we have batch size 2, we have 5 slices, so we trained that for two updates now. Not much happened, but what we created here are some weight file. We can look into the header of that. So as I said, it contains multiple CFL files. So the first file is the file for the lambda, so the trained gradient step size. We have 10 lambdas, 1 for each unrolled iteration. We have the weights of the convolution. We have 10 times because we have 10 iterations. And then we have, so of the unrolled network, and then we have a kernel size of 11 by 11, and we have 24 filters. And these are then the weights corresponding here to the radial basis functions. Okay, so that is the basic training, generate weights or optimize weights. You can do the same with Modal. Not much changes, and that is, I think, pretty nice. So one change is that we use the Modal as network, not the variational network. And what we do here is Modal proposes some two-step training. So in the first step, we initialize the weights by training with just one unrolled iteration of the network. And in the second step, we load the weights to do refinement with 5 iterations here. I think in the original paper it were 10. I just run that cell, but that maybe also addresses the question of loading, of working with more data sets. So what you could do is, here we have the -L option, which just loads the weights which are trained with the 1 iteration network, and then retrains on them or initializes with that. So you might have a bash loop which always loads the weights from the previous initialization, from the previous training to do training on multiple files. Yes, and then the output is similar. So again, we have some the reference, I joined the coils, the PSF, and then the weights for the Modal network. Yes. So now that we have the weights for both network, we can just apply them. And what the only thing is we change is that we, instead of ---- train, we have now ---- apply. And we, of course, do not provide any reference now, but some file name for the output file. And we load the weights here. Oh, don't want to move anything. And then we can just visualize our reconstruction results. So on the left, we have the reference, the output of the variational network and the output of Modal. And you see, of course, it did not work very well because we just trained for 2 updates on a very small data set. So let's do that again. I call it here extended training. And the thing is, of course, that takes time. So we will skip that in the demo mode here. But if in the beginning you set just demo to 0, then it will call that command and save the output in some log file, and the log file is only what I print now out here. One interesting thing is that we can also provide the validation data as arguments to our Recognite command. So here with the ---- valid data option, then we provide a pattern, the case space, the coil sensitivity maps, and the reference. And then after each epoch of training, we will get some update based on this, some metrics based on that validation data. So I mean, I can run that, but it just prints the log output here, but you can run that on your local system. And yes, so the output you see here. So starting from here, there's a mean squared error of the magnitude of the validation data set. So you see the first epoch is still higher than in the last epoch, which is of course desirable. and also yeah, some other metrics like mean squared error, mean peak signal to noise ratio, means SSIM, and so on. Yeah, that cell does the same for Modal. So again, we just print with more epochs the output, and we got better weights, and these weights are already stored here in the if I go to webinar 6 in the pre-trained directory, and now we can use that weights for application. Take some seconds to do the reconstruction, but not many, 6. And you see, okay, the trained networks look, or the output of the really trained networks, for me at least, it looks very nice. No, yeah. So that would the basic usage of the reconet command. We have also some evaluation option. So you can evaluate the network by gives the -- evaluation, and then again some reference data. So that will just apply the neural network and compare with the reference data, and then also outputs some metrics on the reconstruction here. Yes, I think you can look at that. So
Moritz, so
yeah.
it's a lot of detail and it looks really great. We have a number of questions.
Yes.
So just before we answer them, it looks like you want to show some extensions, and then there's going to be another demo after.
Yes.
Is that right?
So
yeah. So why don't you just talk about the extensions, and then we can take questions and take a quick break.
Yeah, I think the extensions, it's just that. So the first extension, some options, I think you can go through that. So usually the help command, it prints you some options you have. So we can, for example, configure the training algorithm. We can also configure the loss, which might be interesting. So if we use the train loss, we could say, okay, we want to have 0.1 times the mean squared error as the loss plus whatever, the 0.2 times the mean squared error of the magnitude or something like that. So there we are quite flexible to configure the loss. And here there are also losses which are not really suitable for image reconstruction, but more for classifying. We can configure the data consistency term. So for example, for Modal, we can configure how many CG iterations we want to use. And of course, we can also configure network parameters. So we can say, okay, we want to use more filters in the variational network or more layers in the residual block of the model and so on. So it has a lot of options. You can go through them. And the thing, what is interesting, and I would like to show now, is also the extension to non-Cartesian trajectories. But maybe first we have some questions. John, if you have them in the chat.
So some of them have been answered in the chat. One question was, does normalization work for the volume when you showed normalization? And if I understand, the question is, if you have a volume of data, can you normalize the full volume?
Currently not. I think it's an interesting question. Like if you have a 3D k-space, then it should do that. But I never worked with 3D k-space, so it's not really, I mean, it should work. Everything is generically implemented, but I never tried that, and it might use much too much memory to have convolutions in all 3D, in the 3D setting. But it's an interesting thing that probably if we keep the slices in the slice dimension, it would be interesting to have normalization there on many slices. But currently it's not implemented, no.
But it is the case that if your data set was inherently 3D, then everything would translate to 3D networks, 3D normalization, and 3D reconstruction.
It would, but I never tried that. So you could try that, but I expect that it explodes memory. And so I never tried that on a full 3D data set. But if not, I mean, maybe we could get in contact with anyone who wants to try that and just try it and work together on that.
Mm-hmm. There was a question about how the optimization is done. I'll just repeat what was in the chat. So this is all done in BART using optimization functions written directly in BART. So it's all self-contained in BART. There's no call to any other libraries like TensorFlow or PyTorch. And then the training algorithm here that Moritz is showing is how you can configure different types of optimization algorithms. So reading off, I can see Atom, Ada Delta. So really the things you are probably familiar with from other machine learning packages, SGD, stochastic gradient descent, those are all available here and they're written directly in BART. Another question was about memory mapping. So if memory mapping is, if you don't have enough RAM, then memory mapping will load partially. And there was a question about how this might work with other tools other than Reconet. And Martin answered in the chat that it will do its best to load what it can, as long as it's not all being used for the same operation, but that might slow things down. Oh, there was one other question that was not yet answered. In the model example, do you use the CG calculated gradients as in the paper, or are you using the auto differentiation to calculate the gradient of the CG operator?
We use the CG operator as written as explained in the paper. So we only have the CG, not the automatic gradient. Yes.
Okay, those were all of the questions that I saw. Any other questions, feel free to put them in the chat. You can go ahead with the last example.
Yes, the last example here is the extension to non-Cartesian trajectories. So you can pass trajectories with the minus trajectory option. As a first step here in that cell, we just generate non-Cartesian. No, we again define environment variables, which gives us shortcuts to the file where the trajectory sits and the training k-space and the validation k-space, no radial. So we work with the same data. So we simulate non-Cartesian k-space here with the BART UFFT tool. That was also rather quick. So you should have here now somewhere in demo. Yes, I was again one level up. Sorry. So we have now somewhere we have some radial k-space data given by that environment variable path. So then we need to, so we have it now, yes, here for patient 19, we have the radial k-space. With the next cell, again, we just join the training data to have one large file containing all the k-spaces. And then training Modal is just again the same. We provide the trajectory here, the training trajectory here, the validation trajectory. I feel like it works better if as an initial reconstruction, we don't use the adjoint reconstruction as usually done for the zero field reconstructions or for the Cartesian way, but instead we just use a Tikhonov regularized or a CG sense reconstruction as initial reconstruction for the neural network. And here, we do that with 30 CG iterations. So we can train our neural network for that. Again, skipped here. We perform some, here we have it, some one wavelet baseline reconstruction. So here you see how you could use the BART-Pix tool to have a one wavelet regularization with regularization strength 0 point something times 2. And here we also provide the trajectory, the k-space, which is now the radial k-space, the core sensitivity maps, get some output CG reconstruction. And again, we have the same loop as before, and we join the data. So that might take some seconds. Oh, maybe I skip that and add here again minus G to have it done on the GPU. So that makes it significantly faster. Yes. So maybe John, if something is in the pipeline, then now would be a good time again for a question.
Any other questions that people have? Or comments, things that you think might be useful that we don't have yet? And I just want to reiterate that I think another nice thing of seeing these demos is, we often get questions about how to do different tasks with BART, and these notebooks show great examples of how to string together several different commands, especially when working with multi-slice data, even if you're not intending to do exactly the same pipeline. So use these demos, grab code from it. Hopefully it will help you with your own processing pipelines as well.
All right, it takes a minute. I thought it's about 30 seconds. It takes a minute. Okay, so we have that reconstruction, and we can also apply now the non-Cartesian version of Modal on the same data. I think that goes a little bit faster, I hope at least. So again, we pass the trajectory. Yeah, that went faster. And then we can have here some comparison of the reconstructions. So it was quite strongly undersampled, I would say, with 30 spokes. But maybe one can still optimize the regularization parameter, but for the L1 wavelet regularized reconstruction, I think here it's in that region, it's already too blurry, and here we still see undersampling artifacts. And I would also not call the output of the Modal network a perfect reconstruction, but for me, it looks a little bit better than the L1 wavelet regularized reconstruction. So you can also use Modal, for example, here with the non-Cartesian trajectories. And yes, that I think ends that notebook demonstration. I thank you for your attention. And of course, again, we could have some questions, or Jason will take over and show you how to use TensorFlow priors with BART.
Yeah, thanks, Moritz. This is all really impressive. We have a couple other questions in the chat. I wanted to ask you really quickly, this demo you gave, which BART version is needed in order to run it? Are you checking out the master branch, or are there other versions that also have these tools?
That's now the current master branch.
Okay, so then in a later release, these would be part of the next version. But for now, if you want to use these tools, you need to make sure you're using the latest version of the master branch.
Yes.
Okay. There are a couple other questions. There was a question about whether or not you've assessed quantitative maps after using the reconet command. So if I understand the question is, if you have data that follows, for instance, a T2 decay curve, have you looked at the quantitative values of the maps that come out?
Yes, we started working on that, but I think that will be presented someone else.
Okay,
So
sounds good.
Keep it, see it, or keep it secret to ISMIM.
Okay, looking forward to that. There was another question about how you would train with different trajectories using a single network in this case? Is it supported to have different trajectories in the same training set?
Yes, it does. So basically, you can provide a trajectory for each slice independently. And then you can, like, I mean, that I'm not sure if that is sufficient for the use case we are talking about. But if you have like a different amount of spokes for different slices, you could think about also providing a pattern which then sets, I mean, you will need to have the maximum number of spokes as a dimension of the trajectory and also of the k-space, but you can just set, if you have in one slice less spokes, you can set the k-space corresponding to that spokes to 0 by providing a pattern, and therefore it's quite flexible.
So one limitation is that the trajectory needs to have the same overall dimensions, and then the suggestion is that you could zero out some of the spokes. But if the trajectories are completely different with different dimensions, then they would need to be split into different files for training.
Yes.
Is that correct?
Yeah.
Okay. Yeah, this was really great. I think there's a lot of great info here, and again, you can run this on your own in Colab. Before I hand it off to Jason, I'll just suggest that we take a 5-minute break. And so how about we pick it back up at 7 after the hour. Thanks again, Moritz, and we'll see you after the break.
See.
All right. Let's get started again. I will post once more the link to the webinar Git folder, unless someone can beat me to it. There you go. All right, so I'll hand it off to Jason for the next demo. Once again, you can run the demo through Google Colab. It's free to use. It will give you a GPU. Without further ado, Jason, take it away.
Thanks, John. I hope.
Jason, we lost your mic, I think, for a second there. I think we can. I think we'll hear you now if you speak.
Can you hear me now?
Yes. Yes.
Okay, perfect. Yeah, so I hope everyone can see my screen. And in this Jupyter Notebook, we are going to provide you another possibility, because since a lot of people maybe use TensorFlow to train your model, so we also make it possible that you can incorporate your trained model into BART-Toolbox. So the basic idea is that so the basic idea is that first step, you should have a trained model with TensorFlow. Then you just need to specify those trained model with BART command. Then in this way, you can use the TensorFlow graph in BART. So basically what we need to have for this is that we already have this TensorFlow wrapper function for everything that you need to create tensors and create the TensorFlow sessions, and also to import the exported graph, and also the function to restore the sessions from the saved model, and also to get the operations from the computation graph. And then if you have all of above, you can execute the operation with session.run function in the BART profile, in the BART source file. And but if you want to compile the BART with TensorFlow support, and then you need to download the TensorFlow C libraries. Basically, this is what the TensorFlow wrapper built on. And then you also need a Python program to export graph and also your trained model, the weights. And so here, actually what we can do with TensorFlow computation graph is that you can use it as an regularization term for your image reconstruction. And in this Jupyter Notebook, what you will learn is that we will tell you how to create a simple L2 regularization on image with TensorFlow, then export it, then import it with BART. And also we provide the one pre-trained model and so we also provide you a pre-trained model trained from high quality images. That's prior stuff, that's prior computation graph will improve your image quality. So the first step, just the basic working routine on Google Colab, you need to check your GPU. So to make sure that you can make the GPU is compatible with the BART. So here we got a Tesla K80 GPU, and then you need to set the CUDA libraries. Yeah, then we can start. The first step, we need to download all the files for the whole Jupyter notebook. So we provide you the case-based data. The case-based data is radio sampled, and so we also give you the trajectory files and also the prior, as I mentioned before, and also some Python functions that helps you to export the model and also to read the CFF files. So because in this Jupyter notebook, we are working with TensorFlow 2.4 version. So because sometimes the default TensorFlow version provided by the Google Colab, it always the newest one. So here, the first step, we need to install the version we want to use. It take like over 1 minute. It's a little bit time consuming. And here just a small tips, because maybe on your own working environment that you have your own TensorFlow version. So like so sometimes it's not necessary to install the 2.4 because here it's just for demonstration. If you have 2.8, then for the compiling stage, you have to download the corresponding TensorFlow C libraries. It will also work.
Is there a minimum version of TensorFlow that's needed?
Yes, yes. Yeah, but here we are using the 2.4. Yeah.
And 2.4 is the minimum that's needed, or will it work with older versions?
It should support all the TensorFlow 2 version, I think. Yeah, but for the one, it's not working. Yeah, then you have to, then after we install TensorFlow, then we need to import the TensorFlow with compatible mode. So you have to import v1 because we want to use the placeholder function. So then you import the TensorFlow libraries. Yeah, and basically here you have to specify the placeholder for the image. So here, because we have the image shape 256, and also we specify one variables, we set it to be 1, and we just make sure that our model also have an variable. It's just a dummy variable. And yeah, then we could use the L2 loss as a regularization term on the image. Yeah, then you define the output. Here, one thing you have to keep in mind is that like you have to, because actually the place code, the X is the input of the whole model, then you have to keep the name to be input _0, and for the output you have to keep to name like this, output _0, because this is how we find the input and output in our TensorFlow wrapper function. And then you have to define the gradient of this of our output with respect to the input. Then you need to use the gradient function here. Yeah, and you also to make sure that you have to give the name to be grad _0. And then you can use the function to export model from the utis.py, a small measure, then you can export the model you just created. And then you will find your exported model here. We have an L2 toy. So basically, it's just a very, very simple L2. And then you need to download the TensorFlow C libraries.
Jason, really
Mhm.
quickly, so
Mhm.
the utils.py, is that something that that you wrote, or it's a standard? Is that something that's included in BART?
It's not standard, so I coded myself for myself.
So this is something that if users want to run on their own computer, they'll need to have this file as well.
Yes.
Mhm.
Yeah.
And then I wanted to make another comment that in contrast to the previous demo, right now what you are running is all Python code, and you're calling Python code, and eventually, so you're not using BART just yet. You're just setting up the TensorFlow file that you're saving. Is that right?
Yes. Yeah. Because here we are basically demonstrating how to create a TensorFlow graph for BART. Yeah. So then if we have downloaded the C libraries, we have to specify those variables for the compiling to basically specify the library path and also the library forward. And then we need to compile, we need to get the BART from GitHub, get the source code from GitHub. Yeah, then we need to compile. Here you have to set up your configuration files for compiling. So you need to specify the TensorFlow flag to be 1, and also the libraries forwarder with the variables TensorFlow base. Yeah.
So here, are you compiling, when you set TensorFlow equals 1, is this also compiling with CUDA?
No, currently we have issues with how to make the one GPU shareable, both for TensorFlow codes and the BART codes. So here actually the BART part doesn't support the GPU.
So you're compiling BART without GPU support, but because you're using TensorFlow backend, it will run in GPU.
Yes.
Mhm.
Yeah. Yeah, and okay, the compiling is done. Then the set the toolbox path, and also to add this to the environments. And then we can check our BART version. Oh, no, we can check our BART version. Yeah, it's version 0.7. And we can, because here we are because here the regularization, the TensorFlow graph is used as a regularization term for pix command. Then we can check the command usage information for this TensorFlow computation graph as regularization term. Here, basically, then what you need to specify is just specify with TF keywords and specify the path of the trained model and also the computation graph. And the lambda is this penalty parameters for the regularization term. And yeah, and then basically the regularization term is like more like to optimize this formula and to update your image. So, and for the TensorFlow-Regularizer, actually we use the gradient of this Rx to update our image. So this is why in the very beginning we have to use the TensorFlow.gradient function to define the gradients for the for the computation graph, for the whole computation graph. And then we can start with the experiments, because now we already have a computation graph. And basically here we can use 60 spokes for our demo. And then we use the extract command to extract the 60 spokes from the prepared k-space files and also the trajectories. And then we can use the NUFFT to grading the non-Cartesian k-space data. And after this, we use the esprit to estimate the cosensitivity maps. Yeah, then we can use the L2 toy we just created here. So here, if you get a GPU K80 on the collab, because there are some problems with the GPU here, it doesn't support the TensorFlow with this Q diversion. So you have to disable the GPU, because unluckily I got the K80 here. It's too old. And then the most important thing here, we use the keywords TF, because we already create, we say we already have this TensorFlow toy here, the L2 toy, basically here, L2 toy. And you just specify the L2 toy and also the penalty parameters. And then you give the trajectories, k-space, cosensitivity maps. This L2 pix TF will be our reconstruction. Yeah, and then let's see. And then you can say, oh yeah, the TensorFlow loss. Oh, here is it's not loss. Here is the penalty parameters, and they say, okay, the TensorFlow graph loaded from this file, protobuf file, and then we created the session, and the session we started from this model, and then we use FaceTouch to do the optimization for the whole reconstruction problem, and then yeah, we run for 100 iteration. And then we can compare the results with the built-in L2 regularization. Yeah. Yeah, here the built-in is faster. Then we can compare the results. Actually, it's quite close. Yeah, then we can move on with the second example. We have an log likelihood term. This term will apply prior knowledge that is learned from high quality images, and will boost your image quality for the reconstruction. So if you are interested in this, you can go to the reference to know some details how this term can be used to boost your reconstruction. And so basically this is all the definition of this log likelihood term of the image. And also we prepared a trained model under this prior folder. Basically this is a Peterson model trained with this log likelihood term. And here we have also the computation graph and some parameters we saved here. Yeah, and for the radial trajectory for this model, we use the density compensation. So we also generated the density compensation. We generated a ways for the density compensation for the fix command. Then we can continue with the pre-trained model. Yeah, here you need to specify also the model name, the Peterson, and we put here. Then we can run it with the density compensation, and then also the same trajectory k-space file and query sensitivities. And then let's see. Oh, this won't work because we're not lucky. You say because here the GPU doesn't support the current TensorFlow, I guess. So we have to disable the GPU and it can run. But then because this model is much more complicated compared to the L2 we had just now, so it will take very, very long to run this without the GPU support. Maybe 10 minutes. But we provide you the, but we still have some results that I had with our local machine. So you can say here actually, if you have the prior information that you learned from data from the images, actually it can improve the image quality a lot. Yeah, and also we basically to here we already should we already showed you how to create a computation graph with TensorFlow and then how to work with it and how to make the TensorFlow computation graph can also work with the BART. So basically that's all. Thanks for your attention.
Thanks, Jason. I have some questions that I can ask, but also I want to invite the listeners, if they have any questions, feel free to unmute yourself or ask in the chat. So one question I had is, since this is using the pix command directly, and the TensorFlow component is running on GPU, what will happen with the data consistency component? Will that be running on the CPU or on the GPU?
Sorry, can you repeat your question?
Yeah, so the TensorFlow graph you built, you said that if you set CUDA visible devices not to -1, it will run it on GPU. But what about the data consistency component of pix? Is that running on the CPU?
So basically, I think the TensorFlow libraries. So then we could go up. When you exporting the computation graph, you can specify you want to use GPU or you don't want to. But if the libraries have GPU support, it will take the GPU, just ignore all the settings. So
I think the BART part runs on the CPU.
Yes.
So TensorFlow will copy automatically to the GPU, execute there the TensorFlow part, and then copy back.
Got it.
Yeah, yeah.
Okay. And another question I had is if you are able to use multiple regularization terms, for example, having one of them be the TensorFlow loss, but as well, could you add L1 wavelet or total variation or other losses that BART supports?
We haven't. Maybe we can test this here.
It should work.
Yeah, because we haven't tested this.
Yeah, I mean, now it's still running, right?
Yeah.
Yeah.
You can
And
test
I
it
think you
later.
need a
It should work.
-R after the -L1.
Yeah, I think you need a R option, but you should be able to combine several R options. Also with the TensorFlow.
Yeah, so that's one of the nice things here is that you're adding TensorFlow to BART, but you still have all of the BART fix options that were there before, so they can be nicely mixed and matched.
Right. I mean, what Jason implemented is now the regularization part, but this wrapper essentially could be used also for other stuff. So we haven't really used it, but we could also use it for the model part, data consistency part, or like integrate TensorFlow at in other places in BART, basically. So this is basically just one start on how we could integrate TensorFlow in BART for regularization. Could be extended.
Yeah, that's great. And then just to reiterate, this demo is really nice that it's running in Colab, but sometimes Google Colab doesn't give you the best GPUs. So it's always recommended to, if you're using this for your own work, to run this on your own machines where you hopefully have good GPUs, and then you would be able to get the type of performance that you would expect from running these models on GPU.
Okay, Jason, how long does it run on a GPU?
Without GPU, it's 10 minutes, I guess. I don't think we have the, yeah.
Yeah, but with GPU, it's like a minute or something, or even faster.
Yeah, if with the GPU, then like half minute. Yeah.
All right. Are there any questions from the audience, or has anyone tried this tool out before? I'd be really interested to get feedback. Okay. Anything else, Jason, that you want to add before we sign off? Or?
And to just also maybe an advertisement, we are also going to release a package to people how to train some models with TensorFlow. It's just basically a Python package, and we will also to put the export command there, and then you can train the model with your own image, and then you export, then you can use it with BART.
Yeah, that's really great. One of the things I really like about BART is the ability to mix and match with other languages like Python. And it's nice to now have these machine learning libraries supported as well. So we don't want to tell you how to use BART. We want you to use it in the best way that works for your workflow. And that might be pure Bash. It might be a mix of Bash and Python. And it might be with these other libraries as well. So thanks again, everyone. Especially thanks, Moritz and Jason, for presenting. And but would be excited to have your feedback on these new tools. Feel free to use the mailing list, and stay tuned for the next webinar. We also plan to hold a BART office hours in the next month or so, where we'll just be online to help answer questions you have about anything BART related. So thanks again, everyone, for joining, and we hope to see you again in the near future.
Thank you very much. Bye.
Thanks for joining.
Thank you. Bye.
All right, thank you.
Bye. Thanks.